Um, Thank you very much, and thank you to the organizers for inviting me and giving me the opportunity to speak at this meeting. So it's a pleasure to be here. It's my first trip to Athens. I will try to do some sightseeing at some point. Okay, so this is a talk based on some work that I've been doing with my collaborator Tim Hollowood in Swansea, and Zsolt Gyongyosi, who's a PhD student there. What I'll be presenting is actually a calculation. So you will see that I will be presenting a very specific calculation in 2D CFT. The motivation for this calculation comes from a series of works and series of ideas that we've been pursuing in the context of black hole evaporation and the information puzzle. But the actual content of the talk that I'm going to give will be essentially a calculation in 2D CFT. That's really what it is. Because the calculation is interesting and there are some puzzles that we don't understand. Okay, so here's the outline of the talk. So I'll give you, to begin with, the basic motivation for why we did this calculation. And the context is the information loss puzzle for black holes, and particularly the idea that somehow information retrieval from black holes is related to the idea of post-selection or projection, an idea which usually comes when we do measurement in quantum mechanics, and that results in a projection onto some state in the Hilbert space of the theory. And then I will talk about describing this idea of projection and post-selection. That's the pointer. In 2D CFTs. So I will promptly move away from gravity and go into the more comfortable setting of 2D CFTs where we can do computations. And in that context, I will discuss the idea of a local quench, which is to create a disturbance, a local disturbance in the CFT in this projected state. And then I will describe a computation of Renyi entropies, entanglement entropies, and in particular Renyi entropies associated to these local excitations that are produced in the CFT. And then we'll compute what I will call the efficiency of teleportation. And we'll see that there is a puzzle that emerges in the limit when you take the n that labels the Renyi entropies and you take it to the limit n goes to 1 in order to compute an entanglement entropy. You get a puzzle which we don't completely understand. We don't know what its resolutions are. And then I will point out some large C observations if I have time, and then summarize. Okay, so the overall bigger motivation is in the context of black hole information, and this idea of post-selection or projection is something that made its way into this subject very early on from a paper by Horowitz and Maldacena, where back in 2003, where they proposed that one possible way in which you can understand information retrieval from a black hole, or the fact that the Hawking process actually is consistent with unitarity, is that in the final at late time in a Cauchy slice that is close to the singularity, there's some kind of projection. There's a boundary condition that projects the quantum state of the system such that the information about the degrees of freedom or the of the infalling modes behind the horizon gets teleported out to the Hawking radiation. So the idea is that at late times, at a Cauchy slice which approaches the singularity, there's some kind of projection operator which acts on the, so here in this picture, what you can see is, to set the stage, A here represents a Hawking mode, a mode of Hawking radiation, which is maximally entangled with a partner P behind the horizon. And V bar represents an infalling mode. So V bar, I use the notation V bar because later on in the CFT, V bar will correspond to a left moving or antichiral excitation, and so that's my notation. So V bar here corresponds to left moving modes, A a Hawking radiation mode, and P its maximally entangled partner behind the horizon. So the idea is that of the final state projection is that towards the end of time, there is a projection such that the projection operator which acts such that it acts on the Hawking partners and the infalling matter, the system of the Hawking partners and the infalling matter, in such a way that when it acts on the wave function for the semi-classical wave function, this action teleports the information of the infalling modes into the Hawking radiation outside. So it teleports the information of V bar into A, which is the Hawking radiation. Now, this was a nice idea, but there are problems with this proposal. First of all, if such a mechanism actually operated, it would mean that there is instantaneous transformation, instantaneous, what do I write here? Instantaneous or acausal information transfer from the interior to the exterior. And in addition, this projector, we don't know what it has to be, because in particular it has to be extremely fine-tuned in order for 100% efficiency, in order for all the information on the infalling matter to be transmitted outside. This projector has to be something really special for it to achieve 100% efficiency. But the main problem here is that it would be something that violates causality and locality. Now, more recent developments in the context of the information puzzle have actually revived this idea in a more refined form, in a form that's more palatable. And this is basically the idea that as a black hole evaporates, the Hilbert space, the dimension of the Hilbert space associated to the black hole, which is effectively the microscopic Hilbert space, at a particular time, which we call the page time, the dimension of this Hilbert space becomes smaller than the semi-classical Hilbert space, which is actually the Hilbert space of the radiation degrees of freedom. And so if we are trying to understand how information retrieval or unitarity works in the semi-classical picture, we have to recognize the fact that the map from this effective Hilbert space, which is the Hilbert space of the effective theory, semi-classical theory, the map from the effective Hilbert space to the microscopic Hilbert space actually involves a projection. So as the system evolves in time, this map is what we would call a non-isometric map. So it's some unitary transformation followed by a projection. But this is not a drastic projection as in the case of the final state proposal. It's an incremental process. So it's incremental projections, and therefore the idea is that at the semi-classical level, not at the microscopic level, at the semi-classical level, if you want to think about the information recovery from black holes, you have to think of you can think of this as teleportation, but is kind of incremental teleportation as the system evolves. So that's the idea. So that the process of information recovery in Hawking radiation is an incremental projection process. So since we are talking about the semi-classical or the effective description, we are talking about field theory degrees of freedom. So a very natural question then to ask is, can we study this kind of projection and teleportation just within CFT or in field theory? Okay, so that's what we will do. First, let's talk about a couple of things quantitatively. How do we want to characterize this teleportation of information? Well, so the most natural thing to do is you look at this infalling mode. We can call that a diary, as is customary in the literature. You throw a diary into the black hole, but you want to maximally entangle this diary with an auxiliary system, which we will call V. So V and V bar are like bell pairs. So that's the way you want to think of them. And then you want to calculate the mutual information in the Hawking radiation and V, the entangled bell pair. If you find that the mutual information is 0, which is what you will find before projection, there's no information of V or V bar in A. Now, after this projection, whatever it is, you should find that if information is starting to get recovered, then you should find that this mutual information should become non-zero. And if the information is completely retrieved, the mutual information should become twice the von Neumann entropy of this diary V that you have thrown in. And that just follows from the definition of the mutual information. So mutual information of A and V is entropy of A, von Neumann entropy of A, plus von Neumann entropy of V minus S A union V. So when projection happens and V bar, or at least portions of V bar are returned into A, or if all of V bar is returned into the Hawking radiation, then A union V bar, the A union V, Hawking radiation union V, will purify V, and so then you will find that if you compute this, you get twice the von Neumann entropy of the diary. Okay, so that's a very nice way to characterize this. So this is the kind of thing we want to compute. Actually, we compute something slightly different, and I'll tell you why in a minute, because it's visually more appealing. The entropy of the diary is fixed. So in fact, I don't need to compute the mutual information. I just need to compute the difference of SA minus SA union V before and after the projection. This thing is something fixed. Okay, so I'll just remove this and in fact consider this quantity that we call delta S. And this is what we will use to characterize the efficacy of the teleportation. Delta S will be S of A union V, where remember A is the Hawking radiation, V is the diary that we've, or the Bell pair associated with the diary that we've thrown in. And so SA union V minus SA, this is what we'll compute. And so a measure of, this is a good measure of the success of teleportation, because if you think about this schematically, before you do the projection, delta S should be simply the entropy of V alone. And then after the projection, when the information has of V bar has made its way into the Hawking radiation, you should find that this object goes to minus S of V. This is exactly the same information as contained in the mutual information. But the basic idea is for perfect teleportation, this delta S should look like a step function, goes from plus S of V to minus S of V. That's the goal to achieve. Okay, so I want to move completely from all of this to talk about 2D CFT. Okay, so I want to think about 2D CFT, and I want to think about throwing in these kinds of excitations or diaries, and which are like local excitations. So these correspond to naturally some local operator acting on the vacuum state of the CFT, inserted at some space and time point. W and W bar are your left moving and right moving coordinates as usual. W is x minus t, W bar is the left moving coordinate. And I will assume that this operator OW W bar has some decomposition or a chiral decomposition in terms of holomorphic and anti-holomorphic, or chiral and anti-chiral operators. It's quite natural, and where this sum runs from 1 to d. This d here would be what we would call the quantum dimension of this operator, and that would give you the entropy of the diary. So the way you compute the entropy of the diary, imagine that this is like a Bell pair, except you've got d degrees of freedom or d spin states here, and you compute, like, for example, the Renyi entropy for that, and you'll find that that's just log of d, log of the d. So that's the so-called quantum dimension of this operator, and that's also the entropy associated to the diary that we are throwing in. Okay? Yeah.
Quantum dimension always an integer?
It doesn't have to be, and those are the cases I think in CFTs where I can't write down this decomposition. So, but I'm going to assume that this decomposition exists because it's visually or conceptually easier to actually do the analysis. If you don't have such a situation, then you'll have to appeal at some point to the transformation of the conformal blocks under various things that you do, but the result is exactly the same. Okay? Does that answer the question? Okay. Okay, so I'm going to consider this quench in a 1 plus 1D CFT and take the insertion of this point and think of computing expectation values in that quenched state. And that means that we'll be interested in computing correlation functions that involve the operator O and the operator O dagger inserted actually at the same space-time point, but that's a serious problem because then the state doesn't have finite energy. And so in order to make this well-defined and smooth, you want to separate these off a little bit into the complex plane. So you give them an I epsilon. You separate them in imaginary time by a small epsilon. And you can in fact do this computation that in such a state you can compute this expectation value of the stress tensor using the standard Ward identities, and you will find an exact expression. If O is a primary, you will find an exact expression for this expectation value. Visually, what you will find is that when you insert this operator, you will create two pulses, one moving to the left, which is our V bar, the diary that's thrown into the black hole, and V is the bell pair. And these two move at the speed of light, one to the left and one to the right, and they're entangled, maximally entangled, V's and V bars. Okay? Right. Okay, so I've talked about the diary or the quench. My next thing is to talk about projection. How do I talk about projections in a CFT? So so this has been discussed in at least 10 years ago in a series of papers by Rajapur, and they're very interesting papers. I think they're StatMech papers, and the idea is you imagine that you think of your CFT as basically being produced by some discretized spin chain like system, and you take a subset of that spin chain and perform a measurement. For example, measure sigma z, for example, and then you would collapse the spins on those in that subsector into some specific state, let's call it K, and all the other spins are of course left untouched. Now if you think about this, if you think about the initial state before the projection, this is some linear combination of the states along every site. After the projection, it's natural to now see that this state after the projection becomes basically a product of some non-trivial state that's on the remaining sites times some state here which is labeled as K. And basically what you've done by the act of projection is to basically remove these guys from the system. And so a very natural way to think about the act of projection in CFT is to imagine, for example, that you have cut out a slit in the complex plane, if you think about this in Euclidean language. So you cut out a slit and impose some boundary conditions at the lower end of the slit and the upper part of the slit, and that defines for us the ket B and the bra B. So you have a CFT with a slit if you want to study the projected state, and I also want to study a local quench on top of that, which means I have in that slit, in that plane with a slit, I also have insertions of my operators, and I'm now taking care to actually label the chiral and antichiral portions of the insertions separately. So I've got these points here which are light cone coordinates of the right moving or chiral fields, and the left moving light cone coordinates of the barred or the antichiral fields. And the idea is that as time evolves, W bars move to the left, and so the antichiral fields, they enter the projection region, they enter the slit. Yeah, so the antichiral modes enter the slit, and the chiral modes, which are these the right moving operators, they can move from a region where so this region, the blue region, is A, which is basically the system that I'm interested in. So in the context of the black hole evaporation, this A represents essentially the Hawking modes. So the chiral modes can move from a region which is outside A. Sorry, can move from the region outside A into A. And what we want to see is how the entanglement entropies of the system, of, for example, the Hawking radiation and this auxiliary mode V, how they vary as a function of time or as we perform the projection. So here's the projection operator schematically, and what we want to compute is this efficacy or the measure measure of how efficient the teleportation is. So this quantity that I call delta S in the projected state. And we want to compute this as a function of W bar, because W bar is the coordinate of the antichiral modes, and we want to see what happens as you move W bar from outside the projection slit into the projection slit, and how these measures of entanglement change. So the difference that we want to compute is in the entropies of A union V as a function of W bar, and the entropy of A as a function of W bar. So A union V is what you get when the chiral modes are sitting inside V, which means that these points are there. The chiral points are sitting there. And S of A is when the chiral modes are sitting outside A, and so don't include, so V sits outside A, and so you just have the entanglement entropy of A. So I want to compute this difference, S of A union V minus S of A. Okay, so an important point here is that the projection operator does not actually in general commute with the Hamiltonian. And you might imagine that that is the case because if you create a split in the CFT, you know that there will be transients, and that state is not going to be an eigenstate of the Hamiltonian. So what we are going to do, rather than looking at the time evolution of the entire system, we are going to think about the positions of these points, the chiral and antichiral points, as basically parameterizing a one parameter family of states, and we want to compute the entanglement entropies of interest, in particular this delta S, as a function of this one parameter family. Okay, and we want to see what the effect of the projection is. Now, if you want this boundary state B to preserve some conformal symmetry, then it's basically a Cardy state. And if you assume that, we can map this W plane with a slit into a half plane with a boundary. So you do a coordinate transformation, in particular W equals zeta squared, and you can open out the slit into the half plane. So essentially what you have done by introducing a slit in your CFT is allowed yourself to map it to conformal field theory with a boundary, with conformal boundary conditions, which means that you are in BCFT. And so in this BCFT, we are looking at a local quench with these chiral positions of these chiral modes, which are these V's. And then the boundary conformal field theory, correlation functions in boundary conformal field theory are in one-to-one correspondence with correlation functions of chiral CFT on the plane. So you can insert your antichiral modes in the image region. So you can think of this boundary as basically implementing a kind of image condition, and you can map all correlation functions in boundary conformal field theory to chiral correlators on the plane. And so you've got this situation where when you look at the antichiral modes moving into the projection slit, that corresponds to the positions, the corresponding positions of those operators moving up and down along the imaginary axis up to infinity. So the projection is when the antichiral points hit the boundary from the left and move off to infinity. And the chiral points, they can be either in A or not in A. So those are the two situations. And we now want to compute the Renyi entropy of this configuration with these operators inserted. To compute the Renyi entropies, you do the replica trick, which means that you have to compute now not just a two-point correlation, but you have to compute, you have to replicate the system along with a boundary. And the system has to be n copies of the system which are joined along this interval A. And that means you have an n-fold copy of the CFT, and you have a 2n point correlation function to compute. And if you compute that 2n point correlation function, take its log, then you get the required quantities that we need in order to measure the efficacy of this teleportation process. Okay, so here's some technical stuff. There are n pairs of chiral insertions in this picture, and I label these n pairs by W's these W2J minus 1 and W2J, J going from 1 to N pairs of antichiral insertions labeled by the barred guys. And the main point in this calculation is that whenever 2 points are close to each other, 2 of these coordinates are close to each other, you invoke the OPE rule between the chiral fields in the decomposition or the antichiral ones. And the OPE rule basically is this: if you have some VA contracted with some other VA at positions omega 2J minus 1 and omega 2K, and if these two are close, then the result is basically given by 1 over epsilon to the delta, where delta is the conformal dimension, and a Kronecker delta of these two indices. That's basically the only thing that's needed. Okay, so here's what happens when you study this system. So let's look at this. This is the case when this is a picture drawn in this covering space. So when you take the when you do the replica trick, you can use this map z to the n equals this thing to uniformize this multi-sheeted Riemann surface and take the whole system into the complex plane. So in this picture, what you see is the mod z equals one circle, and the mod z equals one circle is actually the boundary, which is the same as the projection slit. So that's the boundary of the BCFT, but also the projection slit. The coordinates zi and z bar I are basically the coordinates of the antichiral operators. And you can see that this is for the n equals 3 replica calculations. So you can see there's z1 bar, z2 bar, z3 bar, z4 bar, and z5 bar, z6 bar. So when the operators are yet to hit, have not yet hit the projection slit, the antichiral operators, you can see that they are close to each other according to this. Z1 bar close to Z2 bar, Z3 bar close to Z4 bar, and Z5 bar close to Z6 bar. And when they hit the projection, you can see that there is a motion of these operators until actually you see that Z6 goes to Z3, Z4 goes to Z1. This kind of a permutation action. And a similar thing happens for the chiral modes. So when the chiral modes enter A, there is a permutation action on these pairwise contractions of the chiral operators. When the antichiral modes enter the projection slit, there is a different permutation action on these pairwise contractions of the antichiral operators. And you can now compute the correlator, the Renyi entropy, which gives the Renyi entropy. In particular, it gives you what's called the Renyi excess, the effect due to putting the quench operators. And you find that it's actually purely combinatorial result. And the result is given by log dimension, this quantum dimension, times curly d of pi and sigma, where curly d of pi and sigma denotes what's called the Cayley distance, which is the minimum number of pairwise swaps that you have to do in order to relate two permutation group elements. Okay, so when the dust settles, this is what you find. So before the projection happens, when you compute the Renyi entropy of A, remember A is like the proxy for Hawking modes. So this is A, and that means that before the projection, both the chiral and antichiral V and V bar are both sitting outside A. So the entropy here is basically 0. There's no entropy effect. After the projection, which means the mode V is still not inside A, right? It's not inside A. But after the projection acts on the antichiral mode, the diary, you see that the entropy of the region A grows by log D, which actually tells you that as the antichiral mode enters the projection slit, somehow the entanglement entropy of region A goes up by log D. So there is teleportation happening. But then you look at A union V. What happens when you put the chiral operator inside the radiation, inside A? Before projection, if V sits inside A and V bar sits outside A, then the entropy of A union V is log D, because V and V bar are maximally entangled. V bar sits outside A, V sits inside A, so it's log D. But after projection, when you look at this Cayley distance business, what you find is this funny result that the entanglement entropy of A union V, the Renyi entropy actually, is given by n minus 2 over n minus 1 times log D for n even, and is equal to log D for n odd. So completely non-uniform behavior in n, and completely different for even and odd. So if you look at the Renyi excess and compute this efficacy of teleportation, what you find is instead of getting for ideal teleportation, when in the beginning I flashed this slide where this needed to go to from log D to minus log D. So what you see for the Renyi entropies labeled by n is that log D goes to log D over 1 minus n. So if n is 2, for the second Renyi entropy, it looks like you have kind of perfect teleportation. But for all other Renyi entropies, it's imperfect, and that's for n even. For n odd, completely different, log D goes to 0 for any n. So this is distinct from what we would expect for a scenario where there's perfect teleportation. This means that efficacy of teleportation is not 100% for Cardi states. And what's particularly surprising is that the dependence on n is not uniform. And in particular, this is a, well, here I just pointed out that you can do this calculation pretty much exactly, or as exactly as you want analytically, for the free boson system, where you can take this insertion operator to be a sum of exponentials, and this operator has quantum dimension 2, and you can actually show the exact expression, compute the correlator, and show that it interpolates between log 2 to minus log 2 for the second Renyi entropy, but for the higher Renyi entropies, you don't get perfect teleportation. Okay, how much time do I have? Okay, I'm almost done. So here's our attempt to try and see how you can compute the entanglement entropy. To compute the entanglement entropy, you have to compute the Renyi entropies and analytically continue to 1. Now that looks very difficult to do, given that you have such a non-uniform dependence on n. So we try to make use of this approach, which was suggested in a paper by Doker, Dong, and Wu in 2021. And basically what they point out is if you know all the Renyi entropies of a system, then you can form this particular generating functional, e to the minus n Sn plus 1 minus 1 times z to the n over n, sum over n from 1 to infinity. This generating functional, if you look at it closely and recognize that Renyi entropies are just given by traces of powers of the density matrix, this can be written in operator form as minus trace rho log 1 minus z rho over 1 minus z. And this means that if you know all the Renyi entropies for all n, you can compute this sum and compute g of z. And then if you want to extract the entanglement entropy, which is minus trace rho log rho, you take the limit z going to minus infinity of this sum. It's a nice trick, but you have to assume that in z going to minus infinity, there are no singularities or branch points. Okay. Yeah.
Nicely probably, but why don't you take n equals to 1 limit from the odd?
Or just looking at the odd ones. I mean, that leaves open the question of what you do with the even ones. Because if you just, so yeah, there are different options you can take. If you took the odd one, you know the result is just log d. It's not entirely clear whether that's the right prescription to use. Also, what's not clear is whether computing Renyi entropies at integer ends versus maybe you compute them and maybe they have nothing to do with the von Neumann entropy. And the von Neumann entropy has to actually to be computed in the neighborhood of n equals 1. So that could also be the case. So we implemented this procedure, and what you find is that this generating functional g of z for the choice of for the values of Sn plus 1 we get gives you a closed analytical form. The problem is that this expression has branch points along the negative as z-axis, which means that if you want to do the Docker et al. Trick of taking z to minus infinity, you have to find ways of actually avoiding the branch points or choose some prescription, and that's ambiguous. So the n goes to 1 limit is ambiguous, but if you unjustifiably ignore IPIs that come out because there's logs of unwanted, then you find that this, if you compute the mutual information, it gives you precisely log d, but there's imaginary parts that I have thrown away, but it's a puzzle. Don't really understand how to take the n goes to 1 limit. Okay, so here's some observations on large C, because one can compute these, one can do these calculations also in the large C limit. In large C, you use the fact that the correlation function that we are interested in computing can be viewed as a 3-point correlation function in the presence of a twist operator. The twist operator is the one that creates the branch point in your replica calculation. So it's a 3-point function of a twist operator in the projected state. But then that is a 3-point function in BCFT after you do the conformal map. So it's really secretly a 6-point function, 6-point chiral correlator on the plane. So if you take n to be an integer in the large C limit, the twist operators or the holomorphic and anti-holomorphic parts or chiral and anti-chiral parts of the twist operators, they are heavy operators. This is actually opposite to what people do when you're computing entanglement entropy, where the twist operators become light fields because you're taking the n goes to 1 limit. Here the twist operators are heavy, and those other fields have to be viewed as light fields. You can compute the correlator of 2 heavies and 4 lights, and you can compute this efficacy delta S, and you find that actually it does start off positive and then decrease, but it decreases without bound, which is actually one of these characteristics of the large C limit, that the large C limit does not actually see the quantum dimensions of the operators that you are doing the quench by. That's just one of those characteristics of large C, that in the large C limit effectively is like taking the quantum dimension to infinity. So these things never saturate. Okay, so I've got to the summary. So we've investigated teleportation in CFT with a projector onto the Cardi state by mapping to boundary conformal field theory, and we get universal results for the quench, for the Renyi entropies in the presence of quench post projection. What we have seen is that the efficiency of teleportation is less than 100% for Cardi-like states, and there is an even-odd puzzle, and the n goes to 1 limit is clearly ambiguous. There's lots of interesting future questions, not all of which are technically easy to access. For example, understanding the dynamical evolution of the system, the time evolution of the system after imposing this projection, using holography to understand these setups, understanding this kind of SYK information retrieval kind of question in the context of SYK models. Some of this work, especially in the context of holography, has already been done by these guys, the collaborations with Takayanagi et al. So that's all I have to say. Thank you very much for your attention.